With the low cost and versatility of SDA units, they can easily be integrated with other processing units. Benefits of integrating SDA units with other processing units may include reduced carbon footprint and enhanced control over product quality. The size and placement of the SDA unit depend largely on current refinery configuration, feed processed, and desired product slate. Solvent deasphalting can be integrated in a number of flexible configurations with a range of refinery processing units that treat the high-quality DAO, intermediate-quality resin, or low-quality pitch, such as the coker, visbreaker, gasifier, resid FCC, resid hydrocracker, etc. Solvent deasphalting technology is most commonly integrated with delayed coking technology. In this configuration, asphaltenic pitch from the SDA unit is routed to the coker unit to enhance liquid yields and produce petroleum coke. The configuration is especially attractive if fuel demand is low or non-existent. In a grassroots refinery, the cost of using integrated SDA and coking technology is about the same as installing just a delayed coker large enough to process the bottom stream, but the integrated option reduces operating cost and coke make while enhancing liquid yields. Additionally, the implementation of a solvent deasphalter to be integrated with a coker offers an attractive revamp opportunity if the coker serves as a bottoms processing bottleneck. A solvent deasphalted with a delayed coker requires a heater capable of minimizing peak heat fluxes to achieve the desired heater run lengths. Online steam spalling should be available to partially remove coke deposits from tubes and lengthen the time between turnarounds. This table shows properties of liquid products and residual components from a case study comparing the operations of an integrated SDA coker scheme to a plant with just a coker and a plant with just a solvent deasphalter to upgrade vacuum resid streams. Note: the properties of the liquid products produced by each of these three configurations are based on the vacuum residue of a heavy Orinoco crude. At a past American Fuel and Petrochemical Manufacturers Q&A session, refiners discussed their experiences using solvent deasphalter bottom streams as coker feed. ABB Lummus Global used a feedstock of vacuum resid blended with 30% asphaltenes and observed accelerated fouling in the preheat train and coking in the furnace, 10% higher coke production, and distillate products with higher specific gravities. Foster Wheeler UOP used a feedstock of neat solvent deasphalter bottoms and observed coke yield nearly equivalent to Conradson carbon residue content, slightly lower liquid yields, and higher gas yields than predicted using vacuum residue feedstock. M.W. Kellogg, with a feedstock consisting of rose asphaltenes, observed coker yields similar to those produced when using virgin vacuum residue feedstock. The integrated operation of visbreaking with solvent deasphalting presents additional opportunities for refiners to improve energy efficiency with heat integration. The solvent deasphalter bottom stream can be processed in a visbreaker, reducing the amount of cutter stock needed to meet fuel oil specifications and producing additional cracker feedstock. Alternatively, when an intermediate resin stream is taken from a deasphalter that is located downstream of a visbreaker, the opportunity exists to recycle some of the intermediate range components back to the visbreaker, which may result in the overall increase in liquid yields as more of the heavy components in the resin feed are thermally cracked to valuable liquids. According to KBR and Shell, positioning the visbreaker prior to the SDA unit is preferable as the SDA unit can be smaller, and therefore less capital intensive to build. The two companies have discussed offering the integration of visbreaking and SDA in the first quarter of 2018. Asphaltenes can be processed in gasifiers to produce steam, power, hydrogen, and chemicals, which was a scheme used by an Italian refiner to produce approximately 510 megawatts of power. The integrated operation of a deasphalter, coker, and gasifier can be used, resulting in similar increased liquid yield and reduced coker capacity as in an integrated SDA delayed coker scheme, but coke can be sent to the gasifier to produce steam, power, hydrogen, and chemicals. The implementation of a deasphalter, coker, and gasifier in one plant will essentially eliminate fuel oil and coke production from bottoms processing, concentrating the very high Conradson carbon residue materials into an even smaller quantity of slags from the gasifier. Furthermore, the concentrated carbon dioxide stream coming from the gasifier makes a good candidate for carbon capture, enhancing environmental performance and process economics. Using the solvent de-asphalter bottoms as hydrocracker feed has been explored. Joint testing between two companies found that high-quality fuel oil can be produced. Another company found that bottoms from an SDA unit can be fed to a hydrocracker, resulting in 73% conversion of NC5 insoluble asphaltenes. Also, solvent de-asphalting technology has been applied as a product treatment and recycle option for slurry phase hydrocracking processes. With this method, the quantity of pitch produced will be significantly diminished by recycling the light and intermediate streams back to the resid conversion unit. Resid hydroprocessing of DAO is also most commonly used to prepare feed for the FCC or hydrocracking unit.